this is the second part. We will continue solving integral questions by applying trigonometric substitution. Look at the second example, please. Here, we should first look at the structure and decide which trigonometric substitution applies here, right? So our structure is like that. 5x is squared minus 3 squared. So this fits to which structure? This is looking like that structure where instead of x, we have 5x, instead of a, we have 3. And this type is solved by using a times secant theta substitution, right? Secant theta. So what should be our substitution then? Trigonometric substitution that will work here is 5 instead of x, we have 5x, and a square corresponds to 3 square, so a is 3 secant theta. Once you choose the correct substitution, the rest is kind of simple because you just take the derivative and then you insert what you have inside your integral. So this is, what is the derivative of secant theta? It is secant times tangent theta, remember? Secant times tangent theta d theta. So instead of 5x, we will be directly writing this. So let's rewrite our integral in terms of theta. 5 dx is written as 3 times secant theta tangent theta d theta divided by, so this is what? This is 5x squared minus 9. Instead of 5x, I am writing 3 secant theta squared minus 9. So what is this then? Here we have 9 parentheses, secant squared theta minus 1. Remember, this is the trigonometric identity that we were using above. This is tangent squared theta. That's why we have 3 secant theta tangent theta d theta divided by square root of 9 times tangent squared theta. So eliminate the square root, you will just obtain 3 tangent theta then, and then you can simplify things. We are lucky, we have lots of simplifications, and what we have at the end is again integral of secant theta d theta, whose rule is like that, ln of secant theta plus tangent theta plus an arbitrary constant. See, of course, now you cannot leave the result like that. You have to turn back to your original variable. So back substitution. Instead of, to do your back substitution, you need to draw your reference triangle. You will create a right triangle by yourself by using the very first line of your substitution, okay? By using this, you can decorate your triangle. What do you see there? We see, okay, 5x equals 3 secant theta, meaning that secant theta is 5x over 3. So what is cosine theta then? Remember, secant theta is 1 over cosine theta. That's why you just take the reciprocal, take the reverse, 3 over 5x. So cosine theta is this side, adjacent side, divided by hypotenuse. So 3 comes there and 5x goes to this side. After decorating like that, you can easily compute this part as 25x squared minus 9 squared root, right? Okay, then ln, read secant theta. Secant theta is 5x over 3. And then read tangent theta. Tangent means adjacent opposite side divided by adjacent side. So it goes like 25x squared minus 9 square root over 3. And that's it. This is your result. Let me use colors here. So tangent theta corresponds to 25x square root like that over 3. So that's it, okay? You gave the result in terms of x. After applying this trigonometric substitution to your integral, you end up with the integral of secant theta, which is a rule like that. And then by using our reference triangle, you need to draw this little reference triangle here, which tells you What is secant theta? What is tangent theta in terms of x? Okay, that's it. Let's keep moving with the next example, if no questions. Any questions about this solution? Okay, then what is next? Look at this example, please. At the first look, you cannot see any square roots, but only when we have square roots, you can apply this type of substitutions, these fixed substitutions. But take a look at this example again. Instead, in fact, there is a hidden square root here with this power, you see? There is this power 1/2 there, 3/2. So this is in fact a square root. It is hidden there. Let me rewrite the integral by writing the square root there. So 4 minus x squared. This is power to the power 1/2 square root. And there is also this power here to the power 3. Okay? So you can rewrite the denominator like that. After seeing the square root there, you can start applying trigonometric substitution. So this fits to which structure? Let's try to understand. This is 3 squared minus x squared. So it fits to this structure, a squared minus x squared, whose applied substitution is a times secant theta, right? Sorry, a squared minus x squared corresponds to a times, not secant, but sine theta, sorry. Okay, then let's apply it. Trigonometric substitution. We fix the substitution as this one. It goes like x equals, instead of a, we have 2 sine theta. Then take the derivative. 2 times cosine theta d theta is dx. And now we are ready to transform the integral in terms of the new variable. Okay, dx is 2 times cosine theta d theta divided by what we have at the denominator. 4 minus, instead of x, I put this, square this. So square of 2 sine theta is 4 sine square theta. Don't forget to put this cube, it is there. Okay, we have something like this. And then, what is this part? What do you have inside the square root? You need to eliminate the square root by converting this part to a perfect square. And you can do this because this is cosine square theta. Of course, cosine square theta is inside the square root. That's why we have divided by 2 cosine theta, right? But with this power, of course, cubed power. And then what we have 2 to the power 3 is 8. There is another 2 here. 2/8 goes out. Cosine theta divided by cosine cube theta. Let's write this down. And simplify. Then what you have is 1/4 integral of 1 cosine square theta d theta. You can rewrite 1 cosine theta as secant theta. So this is in fact secant square theta d theta. And the final line before we apply back substitution. So tell me a function whose derivative is secant square theta. This integral has a root. Okay, you should see this integral as a root. Tell me a function whose derivative is secant square theta. What is that function? That function is tangent theta function. Okay, I am not putting this arbitrary constant c here anymore because it was an definite integral. Now, after I turn back to original variable, I can insert these boundaries, or you can transform the boundaries for x to theta. This choice is up to you. For example, after this line here, by looking at your substitution, you can decide the new boundaries. Like if x is 0, which is the lower bound, what is what is then theta? Or if x is 1, what is theta? You can do it like that and you can find the new boundaries here. Or if you don't want to do it at this step, you can go all the way to the end and you can, after turning back to x, you can use the boundaries for x. Okay, let's do it like that. Let's go all the way down and then use the boundaries for x. So let's say this is theta and let's see what we have here. X equals 2 sine theta. So sine theta is x over 2. How do I decorate it? It is opposite edge divided by the hypotenuse, right? So I should put x here, 2 goes to hypotenuse, I mean this information. So this is 4 minus x squared. And then tangent theta, you can easily read tangent theta here. What is it? 1 over 4 is already there, and tangent theta is opposite divided by adjacent, x over 4 minus x squared. So this is the final result in terms of x, and then now you are safe to insert the upper lower boundaries for x only at this step. If you do it here from 0 to 1, this is completely wrong because 0 and 1 are not the boundaries for theta. Be careful. They are the upper lower boundaries for x. You can only insert those values for x. Okay, then the final result is 1 over 4, insert 1 first, then insert 0, and the result is 1 over 4 times square root of 3. So if your integral is definite, you shouldn't forget to insert upper lower boundaries at the end after turning back the original variable. Okay, that's the result. Any question? If not, I want to move on. So let's look at this example. The last 4 examples are of kind of exam type of examples because they include more than one technique. What do I mean by that? For example, this first question here, you should first apply a substitution and then trigonometric substitution. So here it goes. This is u equals, if you choose this substitution, then du is e to the power t dt. This is exactly du then, so du over, you know, this is what? This is e to the power t squared. So u squared plus 9. Now, after applying one substitution like that, you see that you can solve this example now by trigonometric substitution. So you apply one more substitution, which is the trigonometric substitution. This fits to the structure x squared plus a squared. So instead of x, we have u. A is 3, tangent theta. After applying that, you will handle the question, okay? I leave this part to you, okay? And du is 3 times secant theta d theta. Okay, let's keep doing that. So 3 times secant squared theta d theta, and this is what? This is it. Square u is 9 times tangent square theta plus 9. You know what to do here. Tangent square theta plus 1, which is secant square theta. So you have 3 secant square theta d theta divided by 3 secant theta. After doing this, you end up with the integral of secant theta d theta. You know, this is a rule. Secant theta tangent theta. Be careful, this is a definite integral. You need to turn back the original variable t to be able to insert these variables, and you need to draw a reference triangle to do that. So your reference triangle is u over 3, right? Tangent theta is u over 3. If I put theta here, tangent theta is u over 3, like that. U squared plus 9. So what you have is secant theta is 1 over cosine theta. Cosine theta is 3 over this. So you take the reciprocal of it. Plus 9 square. Okay. This is u squared plus 9 square root over 3 tangent theta u over 3. Still, you cannot insert 0 and ln 4. Why? Because these are the boundaries for t, not u. One more back substitution. Instead of u, you will just insert e to the power t. Ln square root e to the power t squared plus 9 over 3 plus e to the power t over 3. And now, only now, you can insert t is from 0 to ln 4, okay? And then after inserting, you will obtain your result. Any question? Can you understand now? I call it as the exam type of question because it requires one more technique to apply. First, usual substitution, next trigonometric substitution. And the remaining examples are all like this. This one, and the next one. I will leave them as an exercise to you because you should first apply a substitution. For example, what should be the substitution here? It is kind of obvious that you should choose as your u. Then du is 1 over y dy. Let's try to rewrite the integral. This part is du, right? Du over 1 plus u squared. You see, very similar question. You will again apply trigonometric substitution, where u is a times 1 times tangent theta. I will leave the rest to you. Be careful, this is a definite integral. You know what to do. After turning back the original variable, you can insert the new boundaries. Okay, and the remaining 2 examples are like that. So the last 4 examples are important. They are nice questions. You should solve them by yourself. They are exercises for you. If no questions, I want to move on with the last technique of today, which is called integration of rational functions by partial fractions. Okay, so we will exercise on partial fractions technique in the remaining time. Okay, so let us look at the first example here. You should first apply a substitution and then we will be applying partial fractions next. Let's try to apply this substitution to this example. But then this part is du cosine x dx, you see? Cosine x dx, sorry, I think I wanted to write du there, and at the denominator, what do we have? U squared plus u, right? Then look at the denominator. Denominator can be decomposed into 2 linear factors like that. The partial fractions technique is already explained in the lecture video. There are some sub-cases there about how to apply partial fractions. And those cases are in terms of, you decide the sub-cases by looking at the structure of the denominator. If the denominator is a product of linear factors, just like we have here, linear, and this is another linear factor, you decompose it easily by putting constants at the denominator. What do I mean is, this is your rational function. By the way, rational function means polynomial function divided by another polynomial, okay? So this is, the denominator is a product of linear factors. If this is the case, you decompose it in this form. A over u, b over u plus 1. These are the partial fractions of this rational function. So you can rewrite this rational function in this form. All you need to do is to search for the constants a and b. How can you find them? You will expand these 2 parts, these 2 expressions like this, and then you have what? You have a times u plus 1, b times u should be whatever you have on the left as the denominator. It should be 1. And then by inserting the roots here, you can easily find your unknown constants. If u is 0, this part is gone. You have just a equals 1. Insert the other root, which is -1, then this part is gone, but you have minus b is 1, so b is -1 then. If the denominator is a product of linear factors, it is easy to find the coefficients by inserting the roots like that. Then the integral is, instead of integrating from this, from left, you will integrate from right. So it goes like, this integral is like that, and this is like this. A is 1, B is -1 du. I am trying to integrate this. So integral of du over u is ln absolute sine of u plus, similarly the second for the second part. So this is minus ln u plus 1 plus an arbitrary constant c. And then we cannot leave the result like that because the original variable was x. We will turn back to x. U is sine x, okay? So let's insert sine x for all the u's. Okay, so this will be your final answer for this question. So this is a very easy example just to remind you what was partial fractions method about. Okay, it is all about the denominator. If the denominator can be decomposed into linear factors, sometimes it will contain repeated linear factors. Sometimes it will contain quadratic factors, sometimes repeated quadratic factors. These are all possible cases, which are all explained in the lecture video. You know what to do on the right side to decompose it into its partial fractions. Okay, any questions? If not, let me solve this example, which is a bit more complicated. So this is a rational function, right? Polynomial divided by another polynomial. To start applying partial fractions technique, you need to, before start applying it, you need to be careful about the degrees. If the degree of the numerator is not less than the degree of the denominator, which is the case here, you cannot start applying partial fractions. First of all, you need to decrease the degree of the denominator by applying polynomial division. Okay, so we should apply polynomial division first because degree of the denominator is not less than the degree of the denominator, okay? If it is equal or more, you should start by doing the polynomial division because you need a smaller degree on the denominator to apply partial fractions technique, okay? That's why I start doing this polynomial division. So I need to multiply by 9. 9x squared minus, so it is 9x squared and this part 3x plus 1. So let's rewrite this rational function looking at this polynomial algorithm. So 9 comes here plus remainder, this is the remainder, over this part, x cubed minus x squared dx, okay? This is the new version of this rational function. Let me emphasize some parts. 9 comes here, remainder comes here, and then this part comes here. How do I know that the polynomial division is over? Because look at the degree. This degree is less than this degree, which means the division is over. Then you write this form. Okay, how can I integrate this? Now we have this structure whose denominator can be decomposed into some factors. Let's see, what do we have there? 9x squared minus 3x plus 1, the denominator is x squared, x minus 1. You see, I decomposed the denominator like that. And now, look at the structure. This is a linear factor. Is this a linear factor or quadratic? What do you think? Even if it has degree 2, this is not a quadratic factor. Instead, we call it as the repeated linear factor because you can decompose it more like that. So it is in fact x times x where x is still linear. So you call this factor, this, as a repeated linear factor. Okay, now I will explain how to write its partial decompositions. If you have a linear factor, you put just a constant above and write it. But if you have repeated linear, then you do the same, put constant and write, it is repeated, and you do the same till you reach the same exact power here, okay? You keep writing the same expression, you keep using the same strategy, put B, put C, some constants, and at each step you increase the power by 1 till you hit this correct power, okay? This is what you should do if you have repeated linear. Is that okay? And then, time to find A, B, C. How do we do that? We expand all those denominators to this common denominator. So what is missing here is x squared. What is missing here is x times x minus 1, and x minus 1 is missing for the last term. So what do I have? A times x squared, B times x minus 1, and C times x minus 1 should be whatever you see here on the left for the denominator, right? It should be this 9x squared minus 3x plus 1. Okay, if I can find the coefficients from this equation now, I can easily integrate this. Look at how simple the integrations are after finding the partial decomposition. From the right side, integration is so simple. From the left, it is impossible if you don't decompose it like that. Okay, so you can use inserting the roots technique here. For example, if you insert x equals 0, this is gone, minus c is x equals 0, 1. So you solve c as minus 1, I guess. Then insert the next rule, which is 1. This is gone. So I have just a. Insert 1 for x. So a is 9 minus 3 plus 1. So a is what? 7, I guess. To find the final coefficient b, there are no roots. There is no another root here. I used all the roots. So to find b, what you should do? You should insert these values to your equation. Let's insert them. A is 7. I don't know b yet, so b x squared minus b, I did this computation, and c is minus 1. So I just insert it. C is minus 1 minus x plus 1 should be 9x squared minus 3x plus 1. But by comparing the right and left hand side, the coefficients, you can easily find b. For example, what is the coefficient of x squared here? It is 7 plus b. And then you have minus x, and then you have this constant term. 9x squared minus 3x. So from here, you can solve b as 2, right? So we solved all the coefficients like this. And then it is time to integrate. Let me invent some space. Okay, so what we are trying to do here is, do you remember what we were doing? We were trying to integrate this. So this was the original rational function. We wrote it like that by applying polynomial divisions. Now, instead of integrating this, I will integrate from the left. So I am writing from the beginning on. Integral of 9 with respect to x is 9x plus this part. Integral of a is 7. 7 over x minus 1. B is 2. We solved b as 2. And plus c. C is minus 1 over x squared dx. So that's what we have. It is 9x plus 7 goes out as a constant ln x minus 1. 2 goes out as a constant again, ln x, right? Minus So how do you integrate dx over x squared? This is a power function, x to the power minus 2. You add 1 to the power, divide by the same power, so it is minus 1 over x. Another minus is here, so plus 1 over x, plus an arbitrary constant c, as it is an indefinite integral. So this is your result. Any question? If no questions, by the way, if no questions, I want to add some detail here. You know, we take x squared as a repeated linear factor, right? Because it is decomposed like that into its linear factors, x. So repeated linear. But you should see the difference between x squared and x squared plus 1, okay? So this cannot be decomposed anymore. That's why cannot be decomposed. That's why we need to call it as a quadratic factor, because you cannot decompose it into some linear factors anymore. So only then you can call quadratic factor like that. So this is the difference between x squared and x squared plus 1. I just want to show that detail here to you. Okay, that's your solution. Any questions? If not, let's move on. Look at the next example, please. So let's see what we have at the denominator. This is x plus 1 squared, right? So we need to understand that this is a linear factor and this is repeated linear factor. That's why, how do we decompose it? We decompose it a over x minus 1 plus, if it is repeated, you keep writing, plus c x plus 1. At each step, you increase the power by 1 till you hit the right power like this. So its partial fraction decomposition is like that. After finding ABC, you can easily integrate. So I won't do that part. You can, next step will be finding ABC by expanding the denominators to this common denominator. You know how to do that. I explained details in the previous solutions. So let's assume that we find ABC. Then how do you integrate? A times dx over x minus 1 is ln x minus 1. Then b times, similarly, ln absolute sine of x plus 1. And this part is c times, you know, this is x plus 1 to the power minus 2. And it will be evaluated as the power rule. X plus 1 minus 2 dx. If this is u, this is du. That's why u to the power minus 2 du. So it is what? Minus 1 over u. Okay, then this is minus 1 over x plus 1. Okay, your result will look like this. Of course, you need to find what is A, what is B, what is C. Okay, let's move on if no questions about this example. Okay, let's look at this one now. For the first time, we have a quadratic factor here. You see, theta squared plus 1 is not linear. Why it is not linear, by the way? How do you know? How do I know that? It cannot be decomposed anymore because, recall, x squared plus 1 equals 0. What is the discriminant of this expression? B squared minus 4ac. B is 0, 4 times A times C. So minus 4. If the discriminant is less than 0, this means that there are no real roots. Meaning that this cannot be, so no real roots means that is not decomposed anymore. This cannot be decomposed. That's why we call it as a quadratic factor. The word quadratic means that it is of degree 2. 2 quadratic coming from this second power. So if we have a quadratic factor here, which cannot be decomposed anymore. Also, we have something else. It is at the same time repeated, right? So there is another detail here. We have a repeated quadratic factor. Be careful. How to do that? How to decompose it? Let me show you. If you have repeated quadratic factors, while decomposing into its partial fractions, we have something new, of course. It doesn't work as linear factors. Let me show you here. Okay, so if it would be linear, we would put some a over whatever that linear factor. For the quadratic factors, you put a theta plus b form, okay? So theta square plus 1. Let me explain it here. So what if, this is a smaller example that will clarify things for you. X square plus 1. What if our function that we want to decompose is like that? This is a repeated linear, right? Repeated linear. What is this? This is quadratic factor. That's why partial fraction decomposition will go like that. A over x for this repeated linear, b over x squared since it is repeated, plus for quadratic factors like that, you put cx plus d form, not just coefficient, but something like this. Okay, this is the rule. So for quadratic factors, you choose this structure on the left. Okay, we have quadratic factor here. That's why I used ax plus b form. But I need to do something more because it is repeated, which means I keep writing the same structure because I know what to do when it is repeated. No matter whether it is linear or quadratic, I know the strategy when it is repeated. So a theta plus b, I keep writing same structure, c theta plus d over, what should I do here? I increase the power. It is the cubed power, so I will write one more. E theta plus f divided by, now I increase the power by 1 again and I stop. Why I stop here? Because I hit the correct power, which is 3. I write it 3 times by using this very same structure at denominator, okay? This is the correct way of decomposing it. Let me also emphasize that it is repeated. That's why we keep writing it with these powers till we reach the same power, which is 3, okay? So after finding A, B, C, D, E, and F, you can integrate it. I know this is a very fantastic question, which can never appear in a final exam because of the time limitations. But let's say we find all those coefficients and then how to integrate it. After finding A, B, C, those unknown coefficients, integrations will be simple. For example, for this part, let's assume that we find I am just assuming just the same time. Let's assume that we find A as 1 and B as 1. Then what we have? Theta plus 1, theta square plus 1 d theta. Can we really integrate this? Yes, we can, because if you divide this into 2 parts, instead of using the denominator as a common denominator, instead of that, you can just decompose it into 2 forms like that. I write instead of writing over a common denominator, I write separately, which is possible. And then we know how to integrate both forms. Another recall for you. So there is this famous rule. The x over 1 plus x squared is a rule. Tell me, give me a function whose derivative is 1 over 1 plus x squared. What is that function? What is that function? It is an inverse trigonometric function. You should remember it. So arctangent x, okay? But this is an integration rule. You should know it by heart. Very important rule. I mean, this is a rule. Once you see it, you will use it. So the result of this integral is arctangent theta, of course. So what about this one? And the first one can be handled by using a substitution. If you call this part as u, and okay, if u is theta square plus 1, then what is the u? 2 theta d theta. So this part is in fact d theta over 2. So this integral is, 1 over 2 d theta over, du over 2. I am passing from theta to u, du over u, you see? And this integral is something we know. It is ln absolute sine of u. So this first expression is evaluated as ln absolute sine of u, where u is theta square plus 1. Okay? So after finding the coefficients, I just assume here that we found them. The remaining parts becomes kind of simple to integrate. You can use substitutions or you can use well-known results, rules like that. So I think this, I accept that this is a very long computation to find ABCD, but I just wanted to show it to you. What we do when the denominator contains a quadratic factor. Quadratic. We put ax plus b forms to the denominator. And what happens when it is also repeated? We keep writing it like that. Okay. Any questions about this solution? And for the remaining parts to integrate, these are exercises for you. You can just assume some coefficients and the resulting integrals will be some simple integrals to obtain. Okay? If no questions, I want to stop here.